Swayam Prabha. Digital India. Educated India.
So, okay, this is a geometric property. First point to note is shear center is a geometric property independent of loading magnitude. Okay. So, let us say I have some arbitrary cross section. Okay. Now, in this cross section there will be both the shear sigma xy and sigma xz shear stress coming in this cross section, because this is inclined and this is thin wall, there will be a shear flow like this in this cross section. Okay. If you recollect, in our previous lecture when we started bending moment, we defined the torsional moment T as integral sigma xz y minus sigma xy z times dAx Ax, right. Okay. This was our definition of torsional moment about a chosen origin. Now, I want to take a torsional moment about the shear center, okay, not about some origin, but I want to take the torsional moment about shear center. The original coordinate system was y and z like this. Okay. So, now I have to move this by an amount zsc and by an amount ysc. Okay, that is the shear center with respect to the origin chosen to find these shear stresses. Okay, then what happens? Okay, so now what happens when I incorporate this? When I shift the origin, my y star, now I have to compute the torsional moment about T star, or let me define a star coordinate system here. This y star, z star, okay. Y star is related to y as y plus ysc, no, y minus ysc, okay. Now, similarly z star is related through z as z minus zsc, right, okay. So, now the torsional moment about T star, which is integral sigma xz y star minus sigma xy z star dAx Ax, okay, would be integral sigma xz y minus ysc minus sigma xy z minus zsc into dAx Ax. This I can rewrite it as integral sigma xz y minus sigma xy z dAx minus ysc integral sigma xz dAx Ax here plus ZSC integral sigma xy dAx AX here. Okay. Now what happens? This is your initial torsional moment, okay, minus YSC times this is nothing but your shear force Vz, is nothing but your shear force Vz plus ZSC times your shear force Vy. And what is the definition of shear center? The torsional moment above the shear center is 0. So this has to be 0. Okay. Now let us consider a case wherein if Vz is 0, the case that we have been looking at all along, then ZSC is given by minus T divided by Vy. Okay. Similarly, if Vy is 0, that is it's bending about the other direction alone, which we will see subsequently, YSC would be given by T divided by Vz. Okay. Here the positive direction of T is anti-clockwise moment is positive. Okay. Only then from right hand thumb rule you will get the x as the positive x direction. Okay. So that is why you have minus T by Vy, okay, as ZSC. Okay. So this is how you find the shear center. Okay. So basically you find a torsional moment due to these stresses. Now let us ponder a little bit more on why sigma xy does not produce any moment in this case, any torsional moment in this case. Okay. We found that for the channel section sigma xy was for channel section sigma x y was of the form some a naught plus a1 y square or minus a1 y square, right. I can write that as such. If you go back here, you will find that if you go back here, all this is some constant times constant minus some constant times y square. Y is a variable about which this shear stress varies. Okay. So basically this is how sigma xy varies, whereas sigma xz varies linearly with the independent variable which is s in this case. Okay. So coming back here, I can write this as some function of minus a1 times y square, where a0 and a1 are independent of y and z, okay, the coordinate positions. Okay. Now what am I interested in? I am interested in finding integral sigma xy into z dAx. Okay. Now for the channel section this would be integral a naught minus a1 y square dy. Okay. It varies from minus h by 2 to h by 2, okay, into z, which varies from, which is dz, which varies from minus bf plus zcg to zcg. Okay. This is y, this is z. Okay. Y varies from h by 2 to h by 2 and z varies from, this is the cg, this is the cg of the cross section, it varies from this is Tw, the thickness of the web is Tw, and if the center line of the web is at ZCG, it will vary from ZCG minus TW by 2 to ZCG plus TW by 2. Okay. So, now what happens? What is, if I integrate this, I will get it as A0 into H minus A1 by 3 into 2 into H cube by 8, right. Okay. That is this part, and the Z part will be ZCG minus T plus TW by 2 whole square minus ZCG minus TW by 2 the whole square by 2. Okay. So, this will be A naught H minus A1 H cube by 12 into by 2 A plus B would be TW A minus TW into 2 times ZCG. Okay. So, that will be the moment produced due to sigma xz into z dAx. Okay. Now, integral sigma xz into y dAx has to be computed. Ax sigma xz is a linear function in S, which will be this I can write it as some B naught into S, wherein S is measured from here, that is S. So, how is that related to Z? That will be Bf S would be minus Bf plus ZCG plus Z. Okay. Okay. So, that will be B naught into some constant, let us say C naught plus Z dy dz, wherein this y is from minus h by 2 plus Tf by minus Tf by 2 to h by 2 plus Tf by 2, and Z is from minus C naught to ZCG. Okay. So, if I do this computation, what I will get is, I will get it as B naught into Tf into C naught into ZCG plus C naught plus Z square by 2, which will be ZCG square minus C naught square by 2 will be sigma xz into y. Okay. So, now I have to add these two, get the net torsional moment. This will be integral sigma xy into z ax minus integral sigma x z into y dAx. Okay. I have to subtract these two to get the net torsional moment. Okay. That I have to divide by, that is the net torsional moment. So, from here I get ZSC as T divided by By. Okay. This expression will include, will be in fact ZCG plus E, where E is same as what we had computed before. Okay. So, you have to run through these calculations to get through up to this step. Okay. Now, the final thing I want to show you is this integral sigma xy dAx is equal to Vy. Okay. I will show it for rectangular section and you can do it for other sections. Okay. For rectangular section you found that sigma xy is Vy by Bh cube 12 into h by 2 whole square minus y square divided by 2. Okay. So, now let us integrate this. Now, Vy has to be integral sigma xy dA x Ax. So, this will be 12 Vy by 2 Bh cube integrated over h square by 4 minus y square dy integrated from minus h by 2 to h by 2, this entire thing integrated over dz from minus b by 2 to b by 2, because I am looking at a rectangular cross section with this as y and this as z. Okay. So, this is a rectangular cross section with CG here, wherein this distance is h by 2 and this distance is h by 2 and this width is b by 2 each. Okay. So, this will be the 6 By by Bh cube. If I integrate dz, I will get b into h square by 4 into h minus y cube by 3. So, it is 1 by 3 into h cube by 8 into 2. Okay. So, what is this? B cancels, h cube cancels, the 6 into 1 by 4 minus 1 by 12, right. Okay. So, this is nothing but Vy by 2 divided by 12 into 2. So, that will be equal to Vy. Okay. So, basically that is why integral sigma xy dA is equal to Vy. Okay. So, we will stop here for today's lecture. Thank you.